This lesson deals with BJT low-frequency models. You can find these notes in the ECE302 ebook in Chapter 5, starting on page 1. Suppose that we bias a BJT in the active region, and then we allow a small variation in the base emitter voltage. I've shown this in the schematic below. I've got a battery, a limiting resistor, the collector and emitter of my transistor, but between the base and the emitter, I'm applying a voltage that has a purely DC component and a purely AC component. In other words, an average value of 0. The voltage across here, with a lowercase letter with the uppercase subscripts, means any voltage versus time. And we're specifically making this a DC component and an AC component. For the DC component, we use uppercase letters and uppercase subscripts. And for the AC, lowercase letters with lowercase subscripts. This notation is very different than what we did in ECE302 with phasors, but this is a phasor. The collector current that's here, DC-wise, is going to be our Eber-Moles equations from Chapter 3, where we had I sub s times e to the VBE over a to v sub t. This is going to be at what we call the Q point. And I threw away the small terms that were here. The collector current versus time, this again is any current versus time, is going to be our Eber-Moles equation, but now applying our voltage VBE versus time. We're restricting this to have a DC and an AC component, so I'm going to write this as V sub BE at the Q point plus little v sub BE divided by a to f v sub t. When you add exponents, you multiply the functions, and so this would be e to the VBE over a to f v sub t times e to the little VBE over a to f v sub t. But what is this? This is my biasing value of I sub c at the Q point. The collector current versus time is going to have a DC component multiplying something that's also varying with time. What we've got is an AC voltage raised as a power of E. If you recall from Chapter 2 on page 15, we said that e to the x was approximately 1 plus x if the magnitude of x was less than 1. This is going to put a restriction on how big this AC voltage can be, and we'll solve for that in just a minute or so. Let's apply that to this. I'm going to take this equation, which has got I sub CQ, and then multiply that by 1 plus the argument of e to the x, which is going to be little v sub BE over a to f v sub t. If you multiply that out, we get our DC biasing times 1, and then that DC biasing times this expression over here. I'm going to pull out the little v sub BE and then divide by a to f v sub t. Here is a constant multiply something that's varying with time, so that's going to be my AC signal, and here's my DC signal. And again, I can do this provided that this argument is less than 1. And what's the base current? Well, any base current versus time would be any collector current versus time if you're in the active region divided by beta f. But this is our definition of a DC current for I sub b at the Q point. And then here, I've got this divided by beta f. That's going to be my I sub b at the Q point. Again, a DC term, then multiplied by this AC term. You take this and write it the following way. In other words, take this value here. I'll call it little I sub little b. Then write this as 1 over 1 over. Dividing it by a to f v sub t over I sub bq. This looks like Ohm's law. The AC base current is related to the AC base emitter voltage divided by a constant. I'll call that R pi. R pi then is equal to this expression, a to f v sub t over I sub bq. And I could write I sub b as I sub c divided by beta f. The value of this resistance depends on the biasing of the transistor and some constants. And again, this only works as if this is true. In other words, that the AC base emitter voltage is less than this constant. Now, a to f is around 1 for silicon, and v sub t is around 26 millivolts at room temperature. Here's a plot of I sub b versus VBE. So we've got this exponential equation. I like to calculate the slope at a point to show a relationship between that and R pi. If I take the derivative of I sub b with respect to VBE and then evaluate it at the operating point, let's see what we get for an expression. We can take our collector current from the previous page in the active region, which was I sub s times e to the VBE over a to f v sub t. This again is any voltage versus time, and then divide that by beta f to get the base current. This is just the constant, so you can pull that out in front. Then the derivative of e to the ax is equal to a e to the ax, and here a is equal to 1 over a to f v sub t. Let's evaluate this at the Q point. Putting in here v sub beq, I have I sub s times this term divided by beta f and a to f v sub t. This is our definition, though, of I sub c at the Q point on the previous page divided by beta f a to f v sub t, and that's the expression over here, reciprocal. In other words, this is equal to 1 over R pi. R pi is the reciprocal of the slope of the I sub b versus VBE curve at the operating point. We're going to call the following a small signal model because we're going to need to make the base emitter voltage fairly small to have this equation work. What we have from the previous page is that if VBE is less than 8F E sub t, then any current and any voltage in our circuit could be approximated by the summation of a DC component and an AC component, like we talked about in Chapter 2. On the previous page, we saw that VBE was equal to R pi times I sub B. And the collector current, when we're in the active region, is just a multiple of the base current by the term beta F. Could you build a circuit that has these equations? That's what modeling is. We're taking equations and represented by equivalent circuits and then using the circuits to do the designing. This looks like Ohm's law. If I put a resistor here and put a voltage across it, I'll get a base current. And then the collector current is a multiple of the base current. That sounds like a current-controlled current source. This will be our model for the AC terms in our equations when we're operating in the active region. We're going to find the AC results. We're going to add them to our DC results to predict what happens versus time. What about a small signal model for a PNP transistor? Well, for the PNP transistor, we reverse all voltages and all currents. The currents are reversed on the schematic, but the voltages we have to change the subscript. We calculate the base current. This again would be any current versus time coming into the base lead. That would be equal to the collector current divided by beta F, and we would have the same expression we had on page 1, except that our subscript here for the AC input voltage would be V sub EB. Dividing by beta F, this becomes our DC value of base current, and this becomes a scalar times our applied voltage. And this will be our base current, purely AC. If we write this voltage divided by 1 over this expression, it looks like Ohm's law. We get the same equation for R pi in terms of I sub B coming out of the base and the I sub C coming out of the collector. All this is true provided that the signal is small enough. We'll do some calculations on the next video. And we now express the model. Well, everything is reversed. We're going to reverse the currents for AC, and we're going to reverse the voltages for AC. The same model with our base, collector, and emitter, but when we draw a PNP transistor in the schematic we saw in Chapter 3, we generally drew the emitter on the top, and the reason that they do this in magazine articles and application notes is that they usually show current flowing from the top of a drawing to the bottom, that current coming into the emitter and out of the collector. So let's flip the model over. Between the emitter and the base, I have my voltage and my resistance, R pi, and the current's coming out of here. And then our current source is pointing from the emitter to the collector. This is sometimes called the hybrid pi model, in that we have a combination of voltages and currents, and this looks a little bit like the symbol pi. And these are low-frequency models for BJTs.